Cool. Right. Thank you for having me here. It's a pleasure to actually be here and talk to you guys. I am relatively new to Labview in the sense I only started really working with it in the last year. In depth in reality. However, I used it a while ago on a project I did as part of my doctorate. So for those of you that haven't met me, my name's Chris Knight. I am an application engineer currently for Beckhoff Automation, and I work in obviously Beckhoff UK. Amongst my responsibilities there are our MATLAB Simulink integration, if that's not a bad thing to say here, our Labview integration, and I look after OOP development with TwinCAT. So helping customers with that sort of idea, as well as doing some projects internally and with some of our larger customers to deliver machines. I've been there 8 years now. It feels like a long time. 8 years. And they took me directly out of my doctorate. And my doctorate is really the subject of my doctorate is what I would like to talk to you today, because part of that doctorate was combining Labview, MATLAB, and a control system, which turned out to be Beckhoff, to achieve the engineering goal that I was after as part of my doctorate. A quick overview of Beckhoff, as I now work for them. They were originally, in the same way as Stefan said, his company was originally known as the Radiator Company. Beckhoff was originally known as the I/O Company. Okay, it had a lot of very clever distributed I/O systems, and we'll come on to why I used them later. But it is now a much bigger organisation than that. We have everything from our own IPCs, embedded and full industrial PCs, our own I/O systems, motion control. We are above all else an automation company, so we have our own automation suite called TwinCAT, which again we'll come on to later. And we are now increasing that portfolio with cabinetless designs for machines and vision systems, and expanding outwards from there. Okay. The company is now growing, is incredibly large. So it's based all in Werl, Germany, where all of our manufacturing is done. But we are up about 5,000 employees now, nearly half of which are actually engineers. So it's quite an engineering-led company, which makes it quite nice to work for. We are still only owned by the one guy that started us, Hans Beckhoff, which is quite entertaining when you can literally walk into his office and have a chat with the bloke that invented it all. But really nice, a nice, pleasant place to work, actually. Sorry, skip too far. So the first thing to mention about Beckhoff is the core idea of the technology is PC-based control. The whole point of what Beckhoff tried to do when it started in the 80s was to move away from microcontroller embedded platforms to PC-based systems where the PLC, the motion system, the safety, the HMI, everything was software implemented as modules that could be downloaded into a real-time system, which is TwinCAT. Okay, and that portfolio of software elements is now growing to include kinematics, robotics, vision systems, machine learning integrations, OPC UA. Yes, and it's expanding year on year. It's quite difficult to keep up with, to be honest. There we go. All of that's manufactured in Germany. This is obviously taken on a clean day rather than the way it usually looks. But it's an awful lot nicer here. Everyone brushes up when the people with the cameras come around, don't they? So, but yes, it's all manufactured in Germany by us. Hence, as with every other manufacturer in this world, we've been hit by this part shortages in the exact same way. We're now almost back up to capacity with the parts coming in, so that's a nice thing. But there's still a backlog, so that's a downside. But yes, we are slowly getting there. So, moving on from that, the point of what I actually wanted to talk to you about today was the machine that we created as part of my doctorate. What we were looking at the time was how to save fuel. So my professor was very into peak oil, the calculations around that, and how we could reduce human oil consumption and make savings wherever we could. A lot of stuff's also been devoted at tidal energy, wind turbines, but was always obviously doing the micro fusion reactors and so on and so on. What his concept was to take the things that we know we can't deal with with wind turbines and so on, and to reduce the oil use that they have. So what we looked at was what's known as rubber-tied gantry cranes. They're huge 80-ton structures that operate at most container ports. If you've ever seen any of the news recently about imports coming in for the port of Felixstowe, you'll have seen them. They look like big ends. Yeah, they drive around all day and they lift and lower containers, the lightest of which is about 12 tons and the heaviest is over 50. Yeah, to do that, they use a 500-litre diesel engine. Yeah, and it generates goes through a generator into an electrical room, but then runs a lot of electrical motors. Okay, so actually quite an advanced drive chain. It would be if it was a car, it would be a plug-in electric hybrid at this point, or so not too bad. However, a 500-litre diesel engine is quite a lot, and there was absolutely no regard for regeneration at all, even though it's obvious because you're lowering lots of large mass that you're going to get regenerative energy. The way that was dealt with, if you'll believe this, was resistors the size of me on the side of the crane that burnt white hot when it was going. Yeah, obviously not the most efficient use because you're just generally trying to heat up Felixstowe, which they actually did quite a good go at, in fairness. But our concept was to move towards effectively, if any of you are Formula One fans, a KERS system for a crane, a flywheel energy storage system that would gather capture the energy as the container was being lowered, and depending on when you wanted to use it, release the energy again when the container was being lifted, but to do in a controlled manner. And when I say controlled, not just in terms of electrical release, but in terms of when it was actually being released. So a more intelligent design of when things would be happening in order to allow greater savings than just sort of like the 20% you get from just regenerating all the time. And what we finally settled on design-wise, effectively, was a fuzzy logic control system, because I didn't want to do the maths for a non-linear optimal control system. So a fuzzy logic control system running a motor type called a switch reluctance motor. If any of you are aware of that, it's probably the most efficient form of electrical motor you can get. Doesn't have any windings at all on the rotor side. It is literally just steel plates welded together as a rotor, and it uses the reluctance action, that is metal's natural tendency to align in a magnetic field, to actually produce rotation. Okay, as a result of that, it's roughly between 96 and 98% accurate, efficient, depending on who you use to do it. Benefit of that, obviously, because we're shoving energy into a flywheel and pulling it back out again, those losses count twice for us. So the smaller we can make that number, you're still going to have to times it by 2, but that's only a 4% loss rather than a 20 or 30% loss like an induction machine. Okay. So with that in mind, we needed a control architecture that could actually run a switch reluctance drive at that rate, and then network multiples of them together, taking into account multiple cranes, as well as monitoring the crane to work out what the electrical system was doing on each one. So we settled in the end on a Beckhoff control system. After a bit of research, it was the one that we found that had a number of features, which I'm going to come on to, but primarily at the time EtherCAT, and a MATLAB and Labview integration that I could actually use. Does that make sense to anyone? Everyone, sorry. To anyone? Everyone. Sorry. If you do want to stop me anytime, just jump in and ask questions. Otherwise, it's just me talking, and even I'm bored of that. So the first point, how we got the communications going. The first and most important part of this system is EtherCAT. Is everyone generally aware of EtherCAT? I've never heard of it. Okay, some nods, not many. So EtherCAT is a Ethernet-based field bus that was invented by Beckhoff in the early 90s and then released as an open standard. So there's now something like 6,000 open organizations creating solutions for it. And for motion control, I might say it's biased, but it is the best one to use, right? Because of a number of features. The first being that the network will actually build itself. So gone are the days of having to actually go through, set in IP address names, and actually do a network plan. EtherCAT doesn't actually really care what your network topology is at all. Okay, when you connect a set of EtherCAT devices together, they will auto detect the devices next to them and build a network out of themselves. Okay, And so the only effort you have to go to, and I can show you this on the demo rig later, to get this is to run a scan of your EtherCAT network. It will then return you your configuration, and away you go. That's it, job done. Yeah. So that's quite a significant benefit and a time saver. One of the important points about it as well is that because every single device in an EtherCAT network is an EtherCAT device, that may sound silly, but what I mean by that is there's no sub buses being run or anything like that inside the network. Every single one of these devices can be synchronized to every single one of the other devices for a system called distributed clocks, but it's just a built-in part of EtherCAT. Okay. What that means is that we can be sure when a device generates an output or gathers an input from a sensor, the connected sensor or actuator, to within nanoseconds of each other across an entire network. Okay. To give you an idea of network size, EtherCAT networks are only limited by 16-bit counter, so you could in theory have 65,000 devices on a single EtherCAT network. No one has ever built one that big. Yeah, even we haven't built one that big. I think 10.5 was the biggest one we built, Brad. Yeah, so that's it. If you want to build one that big, feel free. Current lead times are long, so it will take a while, but feel free. So massive advantage to that. The second part of this is the way EtherCAT works. Okay, so standard Ethernet technologies will have IP addresses for each of the devices, and they will send specific data packets out to those devices. EtherCAT doesn't work that way. Okay, the classic analogy is a train going through other stations. Each device is a station, and the train is loaded up by the master with all the data it needs for each particular station. And as the train goes through, it doesn't slow down at any point, and it effectively lobs the data out the window, and the data it needs gets lobbed back in as it's going through, which makes it incredibly fast. Okay, so not only are you talking real-time time temporal determinism on these individual devices in the sort of nanosecond range, but you're also talking cycle times in microseconds if you want to run that fast. Most systems don't, if we're being honest. Most applications run in the low milliseconds, 1-2 milliseconds, right? But if you need to go faster, you can go faster. Our XTS linear transport system runs at 250 microseconds by default. The entire frame is exchanged at that rate. Might be that you've got some really fast input-output response required. You can run the network down at 50 microseconds and get a sub 100 microsecond response, which is pretty quick for an automation system. Yeah. So that was one of the reasons. It gave us that flexibility. We didn't have to worry about where the drives were. We didn't have to worry about what they were named. They could be swapped in and out as we needed to, because one of the benefits is you can just change these devices. As long as it's the same device you're putting back in, the network doesn't care and can carry on running. So it was presented a number of massive advantages. Make sense? Cool. So that's EtherCAT. As I said, no storing forward and no software delays in it. Which left the controller. What did we pick for that? Now EtherCAT is a much more open protocol. There's lots of different options you can go for. Obviously, from the T-shirt, you can tell which one I went for, but with Beckhoff and their IPC systems and TwinCAT technology. So the first element of this is TwinCAT itself. Yeah, TwinCAT's a software platform that we use in order to create real-time executable modules that we can run in a real-time environment called TwinCAT, which then runs our EtherCAT field bus. Okay. From here, we can create anything from PLCs, motion platforms, C++ modules, Simulink modules. We could have multiple PLCs in the same thing. But the main element here is the fact that they are all agreed to follow the same module platform. It was taken from sort of Microsoft's COM principles, yeah, except we call them TC COMs. Right. So same idea. So in theory, if you could program to one of these, you could put any language you like in here. And we do. So we have C++, as I said. PLC, we now have machine learning things that can write directly into it, vision platforms that can also write directly into it. So it's a really useful open environment for me to program in. At the time, I was using text-based languages, so most of that became structured text straight away because it conforms to the IE631 for the PLC systems. So that was useful. And the benefit of that was it gave me that open platform that I could then attach anything else I wanted to. Okay, we'll come on to how I did that in a little minute, but it gave us that runtime that could run an EtherCAT master, run an EtherCAT network at the speeds I wanted to run at to get the response I wanted. So effectively I was doing was shoveling set points out to that switch reluctance drive to make sure that motor was turning the way exactly I wanted it to turn, to optimize the energy going backwards and forwards through the flywheel. Yeah, because obviously every little percentage gain in that process removes a multiple of 2 in terms of efficiency going back the other way once it comes back out as electrical energy. Yeah, and that was the main point of the entire thing. And the implementation of Simulink meant I could create a fuzzy logic control system for this and not have to learn how to program properly. Yeah, and just drop that in there, which was fantastic. Especially as, you know, it's a university project, so it's been done on the shoestring. There's no way I was going on any courses. The other side of that is the nature of the IPCs. Obviously got some demo units here, but what you've got is one of the industrial PCs. So this runs a full OS, full Windows OS, and a compact embedded version, kind of like the compact rear technology, that sort of idea. It's a fully compact embedded system that's meant to go in a cupboard and be locked away for 20 years and forgotten about, effectively. Okay, so they are effectively locked as they are day one after they come off the production line. Whereas these, you might think of them more like a standard laptop. We will upgrade them as time goes on, put later processors in them. So every generation of this becomes more powerful. But with the CX, what we can say is that the same CX can be built in exactly the same way 20 years after the first one rolls off the line. Okay, so you have guaranteed components, guaranteed supply of that device for that length of time, and that was critical in the application we were doing because it was going to go on a crane and be forgotten about, and we we're going to come back 10 years later, dust it all off, and check that it was still working. Yeah, so the whole principle of it was it had to be able to last that long, which meant we couldn't go down this route of industrial PCs, which was just what it is really. That was the application. Okay, so that's TwinCAT runtime on the Beckhoff PC gave me the longevity and the speed I needed. But how to shovel data in and out. Beckhoff originally decided to use a system called ADS, which was their own communication technology that they created to specifically handle non-real-time to real-time communications. Okay, so our runtime here that's actually running in underneath in a kernel has a ADS server, and that's what allows it to talk to the outside world. So ADS is a now completely open protocol. So in the same way as they did with EtherCAT, they created it and then made it open. So anyone can create an ADS server to connect to a Beckhoff device or something else running ADS. We give it away for free, so you can have our implementation of it for free. But what it does is it allows you to connect multiple things together using a standard communication system that is open for anything you like. Most of this is hosted on GitHub, so you can go and download the source code off GitHub to create your own servers. We have a number of customers doing that at the moment. Or you can use our DLL, which is on GitHub again, and that's free or downloadable as a NuGet package. But what that does let me do, or did let me do in this case, is talk from my runtime with all my applications running on it, which were data loggers and stuff, because I needed to make sure what the energy was doing, errors and stuff across on the system on the crane. But it gives me access via the ADS protocol to the outside world. So this block effectively can be anywhere on the planet, and it can be multiple things. Yeah, so you can have multiple routes talking to a system at the same time from anywhere. Okay, which is obviously then the lead into for .NET based programs for our HMI and for Labview and MATLAB Simulink. Okay. So the first bit, as I said to you, I was lazy when it came to programming, and I wanted to do it all in fuzzy logic because that's nice and easy. It's just a little graphs that you move backwards and forwards to make decisions. And I chose to do that in MATLAB because the university had a license for it, effectively. Now, what we are able to do with that, and the beauty of why I chose it, was that TwinCAT can accept a complete MATLAB module and accept that as a TCCOM object, which it then runs in the real time. Okay, so there was no conversion processes, no nothing for me to actually do to get that to work, I could effectively just create something in Simulink and have that running directly on the real-time architecture. And because of the ADS system, I could effectively then create a link back between TwinCAT and my MATLAB Simulink system and effectively create model in loop control. So I could keep updating the parameters in my model and dropping them into the real time to tune the system to give me a better efficiency, to modify the fuzzy logic control to decide when to use the energy in the flywheel better live. Okay, it was quite a useful tool. And it's just going to start when I click it. Nope, I'm going to jump straight past it. It's a really simple system. It is effectively an add-in to the MATLAB Simulink toolchain, which allows me to take the model, as I said there, specify some parameters about it, mostly that I want to build it for TwinCAT, which is what's happening here, and then pour that directly into our development environment. Development environment, you mentioned Visual Studio earlier, Tom. Our work in Visual Studio, so TwinCAT's fully integrated into Visual Studio, which gives us some of the advantage in terms of package management you were talking about, because if you break a project, it will tell you, and that can actually be quite useful. And once the MATLAB system's finished building, you'll end up with what we refer to as a TCCOM object, which you can then bring into the development environment and run as a real-time controller, which is what you'll see here. I do have all this on the laptop. I was aware that obviously some people join me by Teams, so I can roll it out. It doesn't look as good on in small. So you end up with a representation of the block diagram. You can then select a time to run it at. So in this case, 5 milliseconds for the model. And away you go. And that's the tool chain. So it's incredibly simple tool chain that got built. Yeah, and that's what basically saved my PhD effectively. So I was able to, as I say, use most of anything that in Simulink or MATLAB that can be compiled to real time we could use, which meant I was able to use the state-based stuff that they create, the state flow systems they create, as well as the fuzzy logic to actually create a full control system in it, without having to learn all the other stuff, which was quite nice. And it's a really easy drag and drop system in TwinCAT to actually implement it. Then we need to analyze the data. And there were people that asked us why we didn't analyze it in MATLAB, and it was because the person that was doing the PhD for analyzing this data worked in Labview. So I learned Labview, effectively. And it was that simple. And just like MATLAB, we could connect into the runtime using ADS. Yeah. So we now have a set of client VIs which can be dropped directly into Labview itself, which make life a lot easier for type resolution and that sort of stuff. Because one of the big problems going from PLC to non-PLC, we've done in .NET or Python development, is the fact that PLC types are just whatever the IC made up, and everyone else uses a standard set of types and have agreed on them. But can't keep blaming them for just doing their own thing. And what this allows us to do is have TwinCAT running a real-time control system alongside then a system running Labview doing the data and analytics, providing the front end, as it did in our case, of what was actually going on, real energy on a system, and we actually in the end got it to rebuild the model, because once we had ADS into the Beckhoff system, we could actually retune the MATLAB module in Labview, which blew my professor's mind. And retune it using actual live data that was coming off the system, which is actually really cool. Yes. So same sort of idea as the MATLAB video. The difference between the MATLAB integration and the Labview integration is that the Labview is a data gatherer essentially. We can pass data in and out of TwinCAT with Labview, but we don't have a full integration to take a Labview VI and put it into TwinCAT currently. But you can see here a sort of TwinCAT implementation with some variables I've created in a PLC. I've got this on demo over here. We drag in a simple what's called a ADS DAC block, grab some variables that we want from the system. So this made it quite easy to just quickly generate stuff. as we needed to test things. We can specify a number of parameters about it, like the buffer size and so on, that we want Labview to use. We can ask it to bring it in assembled or single or buffer types, indicators, controls, as we need to, and we can even get it to auto-generate stop signals for the for Labview when it's actually executing. As you can see, I did none of that here. Totally bad program practice, but you know, need the demo. So all I did here was create essentially a corresponding set of variables in Labview to what's here. Very carefully trying to count down 10, you might notice, because that's how many was in my array. Enable some of the bits and write to it, and there you have them updating in Labview. So that's what we did. A lot more complicated than this because there was nice fuzzy, because he knew a lot more about Labview than I did at the time, and there was nice graphs. Sort of representations of the flywheel showing an energy level moving up and down it as it filled up and generated back out again. But in the end, it all worked really well together. And then on the live system that we demonstrated, we actually got up over 35% energy savings, which is a lot more than we thought we'd ever achieve, to be honest. Calculated out in numbers terms, we thought that it would save them roughly 3 million pounds worth of fuel a year, and that was back in 2014. So a long time before. I don't know what it would be now in today's money, but it was a lot more. Sadly, they didn't offer to pay us any of that, which was upsetting. But you can't have everything. Cool. And then there's the corresponding write one. So we can actually then use a write block to then grab the elements and drag them and push data back into the PLC as well. Because obviously, just gathering data out of it can be really useful as a data acquisition if we're using Labview as a sort of analytics system, which a lot of our customers do. But actually being able to push data back can also be incredibly useful. So you notice here, and then can then write that into my now Labview front end and update the string variable inside TwinCAT. Works incredibly well. But that's the sort of use case we did for it. So the guy was able to take all the data I could throw out of ADS, set up a nice structure for him so we could grab it all out, bring it into Labview, and then do a lot of maths and wizardry on it to work out what we should be changing to make it more and more efficient each time. Okay, cool. I think I'm still on time, aren't I? Good, just about. That's the end anyway, so you're free now. Oh, there we go. Back to the start. Cool, thank you for your time. If you have any questions, feel free to ask. Otherwise, I'm going to sit down. Yes. Was it to do what, sorry?
Have a lot of things.
Yeah. Yeah, the ADS system can do that internally, so we would just buffer it all into that. It's quite nice. It worked really well. I mean, there was no argument when it comes to throwing things together like that. It was fantastic. As you saw from the short video, it was a drag and drop, and you suddenly have all the data available to you. What he then did with it after that, I didn't understand, but up to that point, I was there. Cool. I'll get out of the way then.
What? But you